actually clue in people as to what we were all chatting about. The smart side was a little bit confusing about homework 1. You could download the assignment from certain parts of the website, but not others. But now it should be, if you click on the calendar item for it, you should be able to download it. If you look under assignments, you should be able to download it too. And the one thing that is slightly not right is that SmartSite only lets me set the due date time of day to within 5-minute increments. So I can't actually set the due time to be 11:59 as opposed to 11:55. But it also tells me what the exact time of submission was, and I am not a jerk about it. So if you turn it in at 12:03 a.m., it's not going to be considered late, so don't worry about it. However, if your homework is, let's see, I will accept submissions up to a week after the due date, and if it's late, and using a reasonable definition of late, then you'll get a 20% reduction in the total number of points, but you will be able to turn it in. But then I won't accept them at all after the 29th. So that's, sorry about that, I don't think I actually stated what the late policy was at any point in anything written down for the course. So that's what it is. And that's going to be true for later assignments too. Basically, you get an extra week for a 20% dock in points. Might as well say this now and then repeat it later. Jing is under the impression that not everyone is starting early on homework 1. I think it gives you the false impression that it's not that difficult to do, but the fact that it's open-ended actually makes it somewhat challenging. And furthermore, the fact that you are using ITK for the first time makes it somewhat challenging as well. Basically, what you're going to end up with, I think, what usually happens for this particular assignment is that you will not write a large number of lines of code, but each one of those lines of code that you do write has to be really has to be debugged, has to be really well written. So that's where people get into trouble. And in fact, the common course of action for students in this course, the kind of, not the top students, but kind of the middle of the pack students, is to get bit really hard on homework 1 and then immediately start on homework 2 so that you don't get bit by it. So usually people, I mean, it's a natural thing to kind of wait until you have to do it and then start working on it. But start early. Start early to avoid these problems. Any questions about administrative things for the course? Homework, discussion, lecture, anything? Okay, good. Today we're going to talk about the problem that I talked about in the very first class, and I referred to it as object detection. And the prototypical example of this problem is that I give you a photograph. I give the computer program a photograph, don't tell you anything about it, and I say, find all of the human faces in this photograph. Or a little bit more specifically, draw a rectangle around every instance of a human face in this photograph. And that's a particular version of the object detection problem, and I'm going to refer to that problem where every object that you're interested in finding is represented as a rectangular block of pixels. I'm going to refer to that as object detection using templates. And so it's just that term, templates. And by the way, if you did purchase the Forsyth book, chapter 22 is pretty good when it comes to this particular area. So the jumping off point for this lecture is what we talked about last time, which is that there is a big set of image processing problems that are phrased in terms of finding correspondences between blocks of pixels in one image and blocks of pixels in another. So again, 2 different frames of a video. We might want to identify that this block of pixels corresponds to this one, to model this person's motion as they're going through a ping pong swing. If we want to detect the cornflake box in a new image and we have a set of training images of it, we might want to set up correspondences between bits of the cornflake box in we could call this the model image, and bits of the cornflake box in the example image. And similarly, if you can identify that bits of one image correspond to the same part of the world or the same 3D object as a certain block of pixels in another image, then what you can do is basically triangulate from the points of view of both of those images to figure out where that part of the world is in a 3D sense. It's the same thing that your eyeballs do all the time to give you a sense of depth. So one very basic question that comes to mind when we think about this problem of finding correspondences between blocks of pixels is, what exactly is the difference between the image patches, or the blocks of pixels? And here are some common problems. Basically, you might think of this as being the easiest case, even though it's not all that easy. In the easiest case, the block of pixels corresponds to the same object, but just taken at different points in time. So if frame 1 of the video is Frank, frame 2 of the video is still Frank. And the only things that differ are the points of view from which you view Frank and possibly the lighting. You can then make this problem more complicated by varying more factors about the world between time 1 and time 2. So at Carnegie Mellon University, they have this, they call it the PI database. It's person identification photographs. So basically you have one person, like this individual, and you photograph them hundreds of different times with different combinations of lighting from different angles and from different orientations. And so if you look at the set of all of these photographs, you'll see that it's the same person, but the pose, in other words, the position and orientation of their face is slightly different from view to view, the lighting is different from view to view, and their facial expression is also different from view to view. So this is to say that you can make this problem of matching patches of pixels across images harder by varying more variables between images. So ideally you can think of this problem of identifying this person across this wide range of lightings and positions as being more difficult than identifying that this block of pixels corresponds to the same one as this one, given that those two images are only a few milliseconds apart. And finally, if you really want to go hog wild and make the problem of finding correspondences between blocks of pixels in one image and blocks of pixels in the other very difficult, you can even abandon the notion that you are actually imaging the same object in both images. And what I mean is, let's say that in one image you have one type of automobile, general type of automobile, so let's say any sedan, and what you want to do is find a correspondence between that block of pixels, which might be of a Honda, and another block of pixels in another image that might be of a Chevy. So this is really making the problem hard, because not only could the lighting of one car be different than the lighting of the other car, and not only could the viewpoint and the position and orientation of the two cars differ from each other, but they might actually be different cars. So this is the general object detection problem, sometimes referred to as object category detection, which is to say, I don't care if they are Fords or Hondas or Chevys or Volkswagens or you name it. I don't care if they're white, gray, or black, or green, or purple. Just find me all the cars. So ideally, this is relatively easy, this is somewhere in the middle, and this is really hard. But you can imagine that finding all of the different objects, no matter what kind of car they are, is a very useful application for things like military applications and security and various things. So here's another one of those arrows that I like to draw, where simple things or really basic things are at the bottom and complicated things are at the top. And this is to say that there's basically a sliding scale of difficulty in terms of how much image patches vary across images. And more generally, if we abandon the idea of finding a correspondence between one specific block of pixels in one image and one specific block of pixels in another image, to the more general problem of just identifying that a block of pixels corresponds to an object category like cars or faces or buildings, then this kind of describes sort of how the problem goes from easier to harder as you add more and more variability. As you go from looking at the same object at two different time points to the same object with different factors like lighting, all the way to looking at completely different objects altogether. And that's what we're going to talk about how to solve for the rest of today. Okay, so that's kind of the problem setting. And here is kind of your take-home message for kind of a general recipe that I would say most of the approaches to solving this problem follow. It goes something like this. First of all, the thing that we do is we decide whether or not we are going to scan through the image and identify and analyze each block of pixels in turn as we scan exhaustively through the image, Or we're going to do that other thing we talked about last time, which is to say, first identify the interesting regions of the image and only analyze those blocks of images, those blocks of pixels in isolation. But once we do that, then we've kind of boiled down our problem of object detection in terms of giving a yes or no decision for every block of pixels as to whether it corresponds to our object category or not. So once you do that, then you've kind of boiled down your problem to something that, at least on paper, is somewhat more simple, or at least more modular, in the sense of just simply having to decide whether a block of pixels, yes or no, corresponds to your object of interest or not. And the overall strategy for how to do that, at least probably 90% of previous approaches for how to solve that, follows this general recipe. The first thing we do is that we take our block of pixels and we rearrange the image intensities in that block of pixels into a vector. So you can think of in a grayscale image, you would have one number for each one of these pixels that tells you how bright it is. Again, we talked about this over and over again, where relatively high numbers corresponds to bright intensities and relatively low numbers corresponds to dark intensities. And let's say that the intensities of these pixels are V1, V2, V3, and so on. Well, the first step that we do is we simply rearrange this thing as a vector, just as you would find in linear algebra. So I'm going to call that vector of numbers V. So then the next thing we do is we consider, or we visualize our set of vectors as living in a high dimensional space. So if each block of pixels has 6 pixels in it, then that vector is going to live in a 6-dimensional space. If you have just 2 pixels in your image block, which is not especially useful, but just imagine that you did, then you would have a 2-dimensional space of vectors where, if you can imagine, the x-coordinate of it corresponds to the intensity of the pixel on the left, and the y-coordinate corresponds to the intensity of the pixel on the right. So that's one of the things you have to do in object detection, is kind of imagine this abstract high-dimensional space in which each one of your image patches lives. So then, living in our high-dimensional space of vectors, each one corresponding to an image patch, we then do this thing called extracting features from those vectors. And in the most abstract sense, you can think of this thing. Is that highly visible or kind of hard to see? I can turn off the other light if that's preferable. Is that more visible, and or are people more likely to fall asleep? A little bit of both. That's what I was afraid of. All right, well, I'll leave it off for just this little bit about the rest of this slide, and then turn it back on. So we can think about, imagine a function that takes a vector as input, f. So the domain of this function is going to be this high-dimensional space of vectors, v, with v in it, and the range of it is going to be some other space. And usually what happens is that the range is a lower dimensional space than the dimension of v. So you can think of this as being sort of a dimensionality reduction or a compression of data from this high-dimensional space of image patches, aka vectors, and compressing that information down into something that's a little bit more manageable. So then once we do that, and by the way, you can also think about this, if you really hold your head still and visualize it, you can think about this as being a transformation from one high-dimensional space to another. So the original thing I was calling the space of image vectors, so that's kind of your space of possible image patches. And the output of this is going to be a space of features, f of v. So that latter thing I'm going to call a feature space. So all of your image patches have been rearranged into these long vectors. They live in a high-dimensional space, and then the feature function basically moves those into a lower dimensional space in some way. Again, as a way of sort of distilling the useful information out of them. So now, our feature vectors, and I also refer to the output of the feature function as the feature vector. So now there's this feature space of for where each one of these dots corresponds to one of our image patches still. And then what we're going to do is classify the feature vectors in their feature space, which is to say, identify portions of this space that correspond to our object of interest and portions of the feature space that don't. So it's basically, you can think about this as carving up a high-dimensional space into sections, some of which correspond to things that look like faces, or things that look like cars, or things that look like buildings, and other regions that don't look like cars, don't look like faces, don't look like buildings. And this process of carving up your feature space is referred to as classification. And for those of you who have taken a machine learning class, this term should be very familiar, and this idea of carving up a feature space into sections should be familiar as well. But we'll talk about it in more detail as we go on. No more red ink. Good. Now, just as an aside, I would like to point out that this general approach, in which we take rectangular patches of pixels and use those patches to represent entire objects, tends to work pretty well for certain classes of objects. And in particular, it tends to work pretty well for objects that appear in the image as more or less rectangular blocks of pixels. So if you look at each one of these individual faces and you approximate it by a bounding box that goes around them, that does a pretty good job of isolating all of the pixels that are part of the face without including too many pixels inside that bounding box that are pixels of other stuff, like the background. There are a few pixels here that correspond to the girl's arm and not the kid's face, but so what? There's not that many of them. Similarly, if you want to do iron detection, you will find that this bounding box, almost all the pixels inside this box, actually are pixels of the iron and not pixels of the vase or the books or anything else. And the same thing is true of the keypad of the old school telephone. So this works pretty well as a general approach for certain classes of objects like cars, faces, and buildings. You can imagine have this same property, that if you draw a box on a photograph of a building, unless it is some kind of strange point of view, or unless it's the Flatiron Building in, is that Boston? New York City, whatever it is, then probably all of the pixels inside of your box are going to actually show you part of the building as opposed to stuff that's behind the building. Now contemplate, for example, what happens if you stray away from objects that are more or less rectangular in how they appear in the image. So there's a whole set of objects that surround us all the time that I like to refer to as wiry objects or limbed objects. And here are some examples of them where really there is no way to draw a rectangular block of pixels that covers all of the ladder and nothing but the ladder. Any one of those rectangular blocks of pixels are going to have a large number of pixels that are actually coming at you from the background and not from the ladder. Similarly for a bicycle, a cart, chairs, stools, those kinds of things. Even people. So if a person is standing at attention, then basically you can imagine representing how that person appears in an image using a tall and narrow rectangular block of pixels. But people don't always appear at attention in images, do they? They sprawl out their body in all sorts of different ways. And if they do so, and you try to represent how they appear in terms of a rectangular block of pixels, you'll actually find that many of those pixels correspond to the fans at the Dodger game as opposed to the Dodger. And you can think of probably your own examples of objects that don't play nice with this idea of being represented by rectangular blocks of pixels. So that's a caveat. But moving on, I mentioned that our first step is to convert our image patches into vectors, V. And then what we're going to do is come up with some function f that takes those image vectors and converts them into some other space called a feature space. In so doing, trying to tease out the important information You might even call it teasing out the discriminative information that basically separates image patches corresponding to your object class from image patches corresponding to other stuff. And so there are basically three general approaches for what this feature function ought to do. One is what's called the invariant approach. So f, the function f, is called invariant to some set of transformations of your image if you always get the same output from f, regardless of how you transform the input image patch within some class of transformations. So just as a very simple example, if I have the same object like Frank, and I make every pixel monotonically brighter, so I just scale the image intensities up by the same amount everywhere, in other words, making it look like I just took a lighting source and moved it closer to him, then you could say, that's okay because I have an invariant feature function. That is invariant to changes in lighting, or it's invariant to scaling of lighting. And if I have a feature function that has that property, then basically what I'm saying is that a bright image of his face and a relatively dark image of his face give me the same feature vector, no matter what. So you can imagine what the possible advantages of this kind of approach are. What it's basically saying is that if you promise me that the image patches will only vary within a certain range of variability, they will always land in the same part of the feature space. And you can imagine that if I can guarantee that for you, then identifying parts of the feature space that correspond to your object of interest versus not becomes a lot easier. Because it's not the case that all of the feature vectors corresponding to the human face or to this particular guy covers some broad territory in the feature space that you somehow have to describe mathematically. They all go into one spot. So that's invariance. And there's a whole literature on feature functions that are invariant to certain classes of transformations. So another approach that is often more practical, but gives you less of a nice behavior, is what's called dimensionality reduction, where here the feature function is only worried about trying to capture the interesting or the salient properties of the object of interest, like the face or the house or the building or the car. There is no guarantee that if I have two images or two image patches corresponding to the same object, that they land in exactly the same location in the feature space. But the notion is that, at least empirically, without any firm theoretical guarantees, that at least empirically, image patches corresponding to faces land in the same general region of the feature space, and images corresponding to other stuff lands in a different general region of the feature space. And as you can suggest, as you can probably guess by the name of this approach, dimensionality reduction, basically what we're doing is using one or another technique to take one of our very high dimensional feature vectors, V, and outputting a feature vector, starting with an image vector that's very high dimensional and producing a feature vector that is lower dimensional than that. So you're essentially reducing the dimension of your image patches. And by the way, there is a whole set of approaches for how to do this, most of which are borrowed from statistics. So, and by the way, just as a kind of meta comment, you will find throughout the rest of this course that one of the recurring themes is that of starting with a fundamental problem in how to process images, how to extract data from images, and solutions to that problem consisting of basically taking an existing tool from another computational domain like statistics or applied math and hijacking it for our imaging related purpose. So actually we already saw this in anisotropic smoothing, where I said basically that there already exists pre-existing machinery for modeling heat flow across a domain, and we basically take those tools and stuff our imaging problem into it. So this is another example of this, where dimension reduction is a very prominent problem in statistics and also in data mining, by the way. And we're essentially going to take the tools that are applied to that and apply it to our object detection problem. So the other approach that is actually sounds a bit dumb, but actually has been applied in practice, is to do no changes to the image patch at all. So it used to be the case that computationally it was simply intractable to try to do classification in a very high-dimensional space. So it used to be you just could not do it. But over the past probably 10 or so years, as more high-dimensional data in more and more different domains has arisen, the machine learning people, or the classification people, have basically brought forth more and more techniques that are applicable for very high-dimensional problems. So, in fact, there are some approaches that simply take the entire feature, the entire image vector V, and classify it raw as is. So this essentially just sidesteps the whole problem of how to condense image patches down to get just their salient information and so on, and just kind of sidesteps that whole thing and says, let's just do one big classification problem and solve that. Yeah?
In the context of like image data, what's like one of the hard, like how many dimensions did we actually use?
So usually the way it works is that you pick a size of image patch, and you're constrained in how large or small that can be. So if you have...
Is that the one where like on the homework it was like the number of pixels in the square you choose?
That's right.
Okay.
That's right. So if you make that square too small, then there's basically no way for it to capture enough information to convey a face versus not a face. And if you make the thing too big, you're kind of necessarily going to include background most of the time. So it's kind of an engineering decision, but general approaches use something like, I've seen in various papers they have roughly blocks of 50 by 50 pixels, more or less. And that's kind of there's no theoretical results about this, but it seems to be big enough to represent faces, but not so big that you include background most of the time. So then what we're really talking about in that case would be an image vector space that is 250 dimensions, and then reducing that down to some number that's lower than that. Any other questions? Okay. So this is, oh, there's that red again. I got to change the color on these things. Oh, thanks. So here is one example of a dimensionality reduction technique that is relevant to you as you go through homework 1. And to illustrate it, I will imagine that we have a really asinine image patch that has only 2 pixels in it, a left pixel and a right pixel. But again, this is one of those situations where there's a complicated, high-dimensional thing going on, and you can get a visualization of how it works by looking at a toy example in a low-dimensional space. So now imagine that my job is to identify these 2-pixel patches that look like a set of training examples that I have. So I start out with a set of 2-pixel images, and I say, these are all images of the thing that I'm interested in. Just work with me on this one. And furthermore, I visualize that set of training images by graphing them on a 2-dimensional plot like this, where the x-coordinate corresponds to the intensity of the pixel on the left, and the y-coordinate corresponds to the intensity of the pixel on the right. So here are just a couple of examples. This guy is bright and bright. These guys would be dark and dark. And similarly, you'd have one bright pixel and one dark pixel, and this one would be the other pixel's bright and the other pixel's dark. So you make this plot that shows what your set of training example, or your example images look like for this object of interest. And you notice a fairly obvious fact that is clear to all of you, which is that more or less they follow a very specific pattern. And in particular, they seem to more or less lie along a line that looks like so. So okay, how can you take advantage of this fact when you are doing object detection in the event that you want to detect a new one of these things? Well, what you can do, you could, instead of describing those image patches in terms of two numbers, the intensity of the pixel on the left and the intensity of the pixel on the right, you could do a pretty good but not perfect job of describing each one of your image patches just simply based on where it sits along this line. So let's just take one example here. This guy would be described in terms of two numbers, again, the pixel intensity on the left and the pixel intensity on the right. But if I simply say, oh, okay, well this image, it's more or less this far along this line. It's not perfectly along the line, it's a little bit off, but I do a pretty good job of approximating what that image patch looks like just by giving you one number, which is where it sits along this line. So you should get from what I just said, kind of where I'm going with this, how you can use this to basically do dimensionality reduction. So then the problem becomes, well, if I am given such a line, then, as I've said, I can do a pretty good job of taking my two-dimensional things with my two intensities and boiling each one of them down to a single number. In other words, I'm reducing the dimension of the patches from 2 to 1. And so the only question that remains then is, how do I decide which line to pick for describing these things? Well, how about we pick the line such that if we project all the points on the line, they have the largest spread. So imagine that you have a line like this, and you project all the points onto it, which means basically you do a very simple gravity-like thing of sucking all the points onto the line in a perpendicular direction like this. They just kind of get like tractor beamed onto the line. If you do that for this line, you will find that the points are distributed all along the line. And in fact, there's a density of points that's very, very dense around here. That's what this curve corresponds to. And it's less dense as you go out, but it has a pretty good spread all along that line. In the conversely, if you were to take a line that goes in this direction, you would, and then did a similar tractor beam projection kind of thing, and crammed all of the points perpendicularly onto this line, you would find that the spread of points is not very large at all. In fact, they're all piled up on top of each other. So it turns out that if you want to find the line that maximizes what's called the projected variance, or the how variable the points are, how smeared they are after you project them onto the line, you can do it quickly and easily using standard tools from linear algebra. And if you do so, then you end up with a line that looks like so. So that's the basic idea behind principal components analysis. And in particular, this line that's shown in yellow would probably be called the first principal component of this data set. In the homework assignment, you will see an explanation of this that is more mathematical, but just to repeat it here, let's say that V is a vector to some point in our space of image patches. So that's V is going to be there. And I have E here is going to be this line that I have estimated by finding the line that maximizes the projected variance. So that's E. So if I simply do what you all, hopefully you've all taken a linear algebra course. Are you familiar with linear algebra? Yay? Nay? Okay, mostly good. Great. So if you simply take the inner product of E with V, then you're basically what you're doing is projecting V onto this line E. An inner product, aka a dot product. So it's kind of, for our purposes, they will be synonymous. And let's say that the inner product of E with V is A, or I guess alpha, either way. So then A, basically, or alpha, does this thing for you where it tells you where along the line the projection of V onto E sits. So A is going to be your descriptor of that image patch. Because it's going to tell you, again, where along this line your approximation of this image patch sits. And again, A dot E, which is this thing, is not exactly the same as the original image patch, but close enough. It does a pretty good job of approximating it up to first order, or in other words, in a one-dimensional approximation. So, if you, and let me make it clear that you can go back and forth. So if you have a line direction E, and you have an A, then you can reconstruct basically what is a first-order approximation to V just by taking A dot E. And if you have your original data V, and you have an E, then by taking the inner product of V and E, you can get its first-order approximation A. So now let's, again, hold our head still and go from the very simple toy two-dimensional example and scale this up into n dimensions. Then basically, instead of having one line direction E, what we're going to do is we're going to have several directions, and they're all going to be called hyperplanes. So in 2 dimensions, you would, or sorry, if the images were 3-dimensional, then you could have, let's see, then you basically have a 3-dimensional vector space. So if you wanted to reduce the dimension, you could have an E1 and an E2 that you project along. And in fact, E1 and E2 would span a plane that you would then project all of your data onto. And if you keep going and add more and more dimensions, add more and more pixels to your image patch, you add more and more of these directions E. So you'd have E1, E2, E3, and so on, which means that you would end up reducing each one of your image patches to some number of numbers, alpha 1, alpha 2, alpha 3, and so on, each of which is the projection of that image onto one of those directions, E1, E2, E3, and so on. So in this sense, you're reducing the dimension of your images, or your image patches, from the full set of pixels V all the way down to some number of these EI. And the thing that pops out of that is going to be these numbers alpha. Alpha 1, alpha 2, alpha 3, and so on. And again, you can still go back and forth. If you have the E's and you have the V's, you can get the alphas, which is your low-dimensional description of the image patch. If you have the alphas and the E's, then you can get what is basically a kth order approximation to your original image patch. Again, this thing, scaled up to k dimensions. And one of the things you're going to do in this homework assignment is actually evaluate the degree to which A dot E is a pretty good approximation of V by basically reconstructing this thing and comparing it to the original image. What you might find is that in a lot of cases, it doesn't take very many of these directions E. In other words, it doesn't take a very large number of numbers to do a pretty good job of approximating what was a high-dimensional image patch. Does this make sense? Okay. Any questions? All right, let's keep going. So this is called principal components analysis. In a more linear algebra terminology, it gives you an orthogonal set of vectors that are ranked by the projected variance. So the first direction, again, maximizes the degree to which the points are spread out when they are sucked onto that line. The second one does the second best job of that, and so on. But they're all orthogonal to each other. And the top k of these directions E give you the best kth order approximation of the V's in terms of this variance. And you can also show that in terms of reconstruction error in a very straightforward sense, the first k of these ordered principal components gives you the best kth order reconstruction error. It turns out that these E's are actually the eigenvectors of a covariance matrix of the V's, which we already talked about when we talked about Harris corner detection. So in fact, it's treating the image patches the same way we treated the two-dimensional vector of gradient magnitudes in Harris corner detection. And if you want to go over that lecture in edges and corners and kind of look at that connection, you can do so. There's another thing called independent components analysis that is another of what's called a linear subspace method. just like PCA, except that the directions don't have to be orthogonal, and you don't have this nice theoretical property that they're sorted and that the first k gives you the best kth order approximation of the image patches. And just as one visual example, PCA, if this is your original data shown in yellow, then basically PCA always gives you orthogonal directions, and ICA may or may not. Well, all right. So I've already said this. Homework 1's available, and start early for numerous reasons. So another approach to dimension reduction is what's called filter banks. So one way you can think about, if you do the math, you kind of write it out, you can show that taking a new image patch V and getting those A's out of it, in other words, projecting the image patch onto your principal components, is basically a convolution operation. It's taking the inner product of each one of your image patches with each one of your E's, each one of your so-called principal components. Now, one of the properties of PCA, which should be clear now, is that for any given data set, or for any given set of example images, you can get a variety, you can get its own unique set of principal components. So if I show you an image of faces, and you do this principal components thing, you'll get a set of face principal components. And if I give you some example images of buildings, you can then get a set of building principal components. So it's data-driven in that sense. The convolutions that you do are determined by this set of example images that I give you. An alternative approach to doing that is to do convolution between the image patch and a set of vectors that are predetermined or that don't depend on the data. So this is called a filter bank approach. In other words, there are no training examples, there are no example images, and you simply put together these things called filters, which are what you convolve the image patch with, and you assemble those things in such a way that they have certain nice characteristics. So, for example, you can look for you can use these filters to identify certain frequency characteristics at different directions. That's what wavelets do. You can use these filters to identify certain gradient characteristics, such as derivative of Gaussians at different orientations and scales. But again, the point is that these are predetermined and they're not specific to any particular set of training data. And here's an example of what's called a Gabor filter bank. It's a particular kind of wavelet. And these are the things that you would, this is the E1, E2, E3, and E4, the things that you would take the inner product with your image patch. And as you can imagine, they identify different frequency characteristics because it modulates up and down like a Gaussian, like a sinusoid. And different ones will have different frequency characteristics and different orientations. And in fact, if you take one of these filter banks and take the Fourier transform of it, you will see that they, in some sense, each one represents a different part of the frequency domain. Each one corresponds to sinusoids at a different scale in terms of frequency and orientation. So, for the most part, I'm going to let you read the slides on this since they're not that difficult to parse. But imagine that we have solved this problem of determining what our feature function f should be. And what we have either done is used invariance, or used dimension reduction, or we've done nothing at all. So basically we have a feature space of feature vectors, some of which correspond to, again, faces, cars, buildings, etc., and other ones of which do not. There are kind of two general, again, this is covered in great nauseating detail in a machine learning class. But I'll just go over two kind of general schools of thought as to how to do the classification part. They're called generative and discriminative. So in the generative approach, you think of an abstraction, which is that there is a probability distribution, or there is some model, some statistical model that is generating these feature vectors. It's kind of an abstraction because that's not really how images get formed. There's no probability distribution living out there in nature that is popping up these images and converting them into features. But it's an abstraction. But if you do that, and let's just say, for the sake of argument, that you say, well, let's consider the possibility that there is a normal distribution, or a Gaussian distribution, that is generating our feature vectors corresponding to the object, and there's another one generating feature vectors that correspond to all other stuff. Then what I can do is estimate the parameters of this probability distribution and compare for any new image patch the probability that it corresponds to our object and the probability that it corresponds to not our object, that it corresponds to any of the other stuff. And if we do that, then we can basically compare those two probabilities to make a decision about whether we are confident that our image patch corresponds to the object or not. In other words, whether that image feature vector was generated by this distribution or by this one. Again, this is kind of an abstraction, but if we think about things in these terms, then we can basically leverage over 100 years of work in the field of statistical inference for solving this problem. The other approach is discriminative. So in the discriminative approach, instead of estimating an entire distribution and making decisions about kind of what shape this distribution is in and what shape this distribution is, we simply look for boundaries. And we estimate sections of the space that correspond to object and sections of the space that correspond to non-object. So in one sense, this is a simpler problem because instead of having to make some kind of a statement about the entire space, all you're doing is trying to estimate what the boundary is. Not that that is especially easy in all cases. And in particular, depending on what your data looks like, these boundaries can be really fairly complex shaped. And here's another example of a complex one. And also, it's not clear what shape the boundary should have until you actually analyze the data. And in the literature, there's various approaches that combine different feature functions and different classifiers. We'll skip that. That's fairly self-explanatory if you read it. But here's a summary. So if you can identify your object in terms of rectangular patches of image pixels, you have to worry about two key components, features and a classifier. And there are a few different schools of thought as to how you do the features and how you do the classifiers. And no one has won the argument yet. I'll just say that there's various features that are still being used, and there are various classifiers that are still being used. Any last-minute questions about this? Okay, great.